SwayamPrabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. So over the last few lectures, as we've been discussing on this topic called root locus, and we've more or less figured out how to draw the root locus for a given system. We know that given a transfer function, we have to massage it into a certain form where it's like some factors of the polynomial, the numerator polynomial and the denominator polynomial. So the transfer function is rational, and we factor the denominator and the numerator polynomials into their constituent blocks. So each of them could be a first order or a second order block. If it's a second order block, it's typically the case that there are complex conjugate roots for that polynomial, and having cast the polynomial in that particular form, we've figured how to apply this so-called angle criteria to determine what points on the complex plane qualify as valid locations for the closed loop poles. In other words, what points qualify as valid points on the root locus. Now, in addition to seeing some of the rudimentary techniques for drawing a rough sketch of the root locus, we also saw a few refinements. So first of all, we saw how we can obtain these locations where there are breakaways and break-ins on the real axis. So we saw that those were actually corresponding to the maxima or minima of the value of the gain k, provided you vary the gain along the real axis. These might also be viewed as points where multiple branches of the root loci, they intersect or collide, right? So that was one. We also saw that there's this thing called angle of arrival and departure, particularly relevant for complex poles and zeros, right? So there we found that again it's tantamount to the application of the angle criteria within an epsilon neighborhood of these complex poles or zeros. Subsequently, we also saw that this angle of arrival and departure idea can be extended to those breakaway and break-in points that we've just spoken about, in the sense that there is this idea called the continuation of the root locus. So let's just quickly revisit that once, short in brief. So for example, you know that this is essentially what we are trying to look for, right? The solutions of this particular equation is what we are looking for. Now notice that if you pose this k as k1 plus k2 as I did in the earlier lecture, then you can obviously write this as 1 plus k1 plus k2 times ns upon ds, right? So we are essentially looking for this. So now suppose k1 corresponds to the value of gain at which this breakaway or break-in occurs, okay? So we can obviously write this as 1 plus k1 n of s upon d of s plus k2 n of s upon d of s is equal to 0, right? So this is then tantamount to writing ds plus k1 ns plus k2 ns is equal to 0. Now suppose you treat this as some d tilde s, right? Because now hereafter this k1 will be kept constant, but you will only be varying k2. So now suppose you treat this in this fashion, then you can write this as d tilde s plus k2 ns, right? So this is tantamount to as if finding the root loci of this, right? Of a plant given by this, right? This is how we can treat this. In other words, we are essentially looking at a modified sort of an open loop transfer function where it is given by n of s upon this d of s plus k1 times n of s, okay. So it is as if this is a fresh start. So this is the idea that we call this continuation of root locus, and we use this to good effect in order to evaluate. So we now treat this sort of root locus as the modified root locus of this g tilde, and then we apply this angle of arrival and departure conditions to the poles. Obviously if k1 corresponds to a breakaway or a break-in value of gain, then obviously this g tilde, if you consider this as an open loop transfer function, this will definitely have some repeated roots, right. It will have some repeated roots in the denominator, in the pole, right. So those poles, if you now try to find out what the angle of departure from those repeated poles are, you can jolly well apply the angle of departure and arrival conditions that we have learnt about, okay. So in combination with this continuation of root locus idea, the angle of arrival and departure allows us also to sketch this root locus to a fair bit of accuracy in and around the break-in and breakaway points. So just as an illustrative case, for instance, we saw this case where there were 3, so suppose there was this point where there are 3 repeated poles, right, and we know that the root locus exists on either side of this on the real line because of the even odd rule that we have already spoken about, one of the early rudimentary rules, right. So now if that is the case, then you know that one of the directions of departure is clearly this, and based on this angle of arrival and departure criteria application, we saw that the roots from this, the branches from this repeated set of roots will have to emerge separated by 2 pi by q angles, 2 pi by q radian angle, yeah, that many radians. So this is the separation between branches emerging from breakaway point, right. So that is the case, and this happens to be one such branch. Then obviously all that you need to do is, you need to, for instance there is 3 here, so then you know that you start from here as your reference, and this is going to be one direction 120 degrees, you go another 120 degrees, right. So that is going to be like another direction, so it is 240 degrees this way, right, and then you go another 120 degrees, which is obviously going to take you back here, right. So that way these 3 directions actually give you the directions of the angles of departure from this breakaway point, right. So that is the important thing to remember from all of this, okay. And finally we also saw for the root locus that how do you evaluate if some branches are actually going from the left half plane to the right half plane, how do you evaluate the points at which this crossover happens? Well, simple, our good old Routh array helps us in that aspect, right. So with all these rules in place and several other observations that we made down the way, now we should be in a fairly good position to draw a reasonably good sketch of the root locus, right, and draw some qualitative inferences. So we started on that route and we saw that we had this typical second order system, right, to which if you add some additional poles and zeros, let's say we took one additional pole and one additional zero, and we saw what effect that had on the closed loop system. So this is slightly different from the effect of pole zero that we studied earlier. Remember earlier we were just talking about this transfer function, expanding it into its partial fractions and looking at the weights on these different factors that we had isolated, okay. So we looked at these residues, right, and we saw that if certain pole is more than 5 times away from the dominant poles, then we can jolly well ignore its effect, right. That was the way we were looking at it earlier. But now this deduction that we made in the last lecture didn't have anything to do with the standalone system, it was about a closed loop configuration. So we saw that if you have, in addition to a second order system, some additional pole and zero on the LHP, right, and if you close the loop around it, then how does the original root locus of the second order system change. We saw that the presence of a pole on the LHP has the effect of pushing the root locus branches to the right half plane, so it is somewhat detrimental. We also saw that the presence of a 0 on the other hand on the left half plane has the effect of pulling the root locus branches. Normally the root locus branches were neutral, right? We saw that they were heading upwards and downwards along the asymptotes, right, with no branches on the real axis. But as soon as you add one 0 on the left half plane, it turned out that it had the effect of pulling the root locus towards the LHP, right, which is something desirable, right. So of course while talking about that, I also said that we withheld the discussions about the presence of right half plane zeros, right, and there is a very good reason for that. Now you see, when we have these transfer functions, the way we write this transfer function for the particular case of root locus problem, in order to sketch the root locus, we write it in this fashion: s minus z1 times s minus z2, as I just said, till s minus zm, right, and then you had, let us say, some k or some a naught, b naught, whatever you call it, right. This is probably the coefficient of the highest degree, so it is bn, right, and then you add s minus p1, s minus p2, so on and so forth till s minus pn. Now notice that if zi comma pi all belong to the left half plane, right, the left half of the complex plane, so this minus sign indicates that it is the left half of the complex plane, right, then there is something very special that you can deduce about this. You can always say that g of 0, yeah, what is this g of 0 going to be? So if you put it in this form, you will see that because when this s vanishes, the minus z1, the minus z2, the minus z3 and all of these terms, if they are real, then because they are on the left half plane, they are inherently negative. So minus of z1 is going to be positive. So each of these individual terms are going to be positive, alright. Suppose they are complex, then what happens? Then when you put s is equal to 0 here, you basically have complex poles appearing as conjugates. So if you have minus z1, you also have minus z1 conjugate, right. So then you see it really does not matter, because it is going to be just minus 1 times minus 1 is plus 1, so it is z1 conjugate, whole z1 with z1 conjugate, that is basically the magnitude of z1 squared, right. Same thing can be drawn about, same conclusion can be drawn about the poles. So it turns out we should only be bothered about those poles and zeros which are on the real axis, or the real poles and zeros and their signs, okay. So if the real poles and zeros are all on the left half plane, that is on the real axis, negative real axis, right, then this g0 is positive, right, and this serves us well. Why do I say that? Because notice again, to reiterate this, what is this g0? This g0 is something that we call a DC gain. And why do we call it a DC gain? DC means a direct current, a constant value. So if you give a constant input, say a step input, then you see that when you apply this limit, I have said this earlier also, so this is just to refresh your memory. So if you apply this s tending to 0, s times 1 by s g of s, yeah, this is final value theorem, yeah, this is just an application of final value theorem. This is going to be y t as t tends to infinity, provided of course g is stable, right. Now obviously this s and s will cancel, so basically it is this g0 that is going to tell you, right. So g0 tells us the steady value to a step input, right. Now obviously if you are applying a positive step, most systems that we can think of, they actually want you to also attain a positive step value. It seldom happens that you, for example, if you are turning your bicycle to the left, you do not want the bicycle to go to the right. If you turn the handle to the left, in fact is just an interesting case in point. There was an experiment that was conducted some years back to see how our brain works, right? And it took quite a lot of training. The scientists developed a special kind of a bicycle which was so designed that if you turn the bicycle's handle to the left, it would go to the right, and if you turn it to the right, it would go to the left. Now those of you who have experience of riding a bicycle would know that the way to balance a bicycle is when you feel it's tilting to the left, you turn the handle a little to the left to balance it. When it's tilting to the right, you turn it a little to the right to balance it, right? Now this bicycle was designed in such a way that you have to actually counteract it, right? You have to do the opposite. So if you're trying to fall over to the left, instead of instinctively turning the handle to the left, you turn it to the right. Yeah, very counterintuitive. So actually experienced bicycle riders, they had to actually learn this. They had to train their brains to sort of act in this counterintuitive way. This old muscle memory and this instinct, loosely speaking muscle memory, and the instinct that naturally takes over, that had to be unlearned. And then they managed to ride this bicycle. But the sad story was that once they managed to ride this bicycle and got pretty good at it, they were demonstrating all of this, then they had very great difficulty in again riding a conventional bicycle, right? So this is just to illustrate that normally every system, if you want something to respond in a certain direction, right, then the gain, this DC gain is better be positive, right? So that's just an anecdote, but the idea is that most physical systems would want you to have, or would rather have, the way they come manufactured, they would have this DC gain positive. Now notice that sometimes you might have zeros, or rather one zero or an odd number of zeros on the right half plane. So for instance, take the case in point that we were discussing the other day. So suppose you have s minus z, an additional 0 added to this conventional second order transfer function, right, with zeta omega n both being positive and z being positive, right. Now notice that g of 0 is negative, right. So in other words, if you try to find out the step response to this system, you will see that if you apply a unit step like this as an input, yeah, your output in the open loop, of course, your output would behave rather in a weird fashion, right. It would behave something like this and would finally probably settle down to some negative value. This is going to be your steady state value, right. So this is going to be your output. Now clearly, as I just illustrated with that example also, this is not something that conventional systems desire. So that is why you will see that when you encounter systems such as this, the conventional way to write this system is to pose it in this fashion, so that it is 1 minus s by z times omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. So usually, so let me write that statement down. So usually transfer functions of physical systems having RHP zeros appear in this form, for the reason that I clearly illustrated, right. So now if it appears in this form, you can clearly see immediately. Of course, this division by z is just a normalization. You can keep the z here if you like, yeah, or you can absorb it with this. It's just a constant gain now, right. So now notice this is now going to give you a G0 that's positive, all right. So you'll see that most physical systems that are designed to respond to inputs in a certain fashion, they would have a DC gain that's positive, and therefore most physical systems transfer functions would come in this form. So if I just modify that a bit, I'm just going to call it, let's say, G bar S is going to be nothing but 1 by Z, Z minus S times omega n squared upon S squared plus 2 zeta omega n S plus omega n squared, right. So then, based on our discussion now, if we want to find out the root locus of this system of G bar, which is actually what the physical system is, right? Actually it is G, I'm just adjusting this, okay. So you can, in fact, if I remove this Z, then you can call it G bar, because notice that G and G bar, the way I have defined it here, G and G bar are just scaled versions of one another, so their root loci will not change much, except for the fact that probably the values of gain, the closed loop gain for one and the other will be scaled by this factor of 1 by Z. But essentially the locations of where the root loci lie, that does not change when you multiply a transfer function by a constant factor. Why? Because the angle criteria is not affected by multiplications by constant real numbers, right. So therefore, whether I look at this G or whether I look at the root locus of this G bar, it really would not matter. But now notice, if I want to study the root locus of this system, I must put it in the conventional form, and the conventional form is not Z minus S but S minus Z. So then I have to write it in this form, right, in this form. Now in other words, what this means is, if I am putting this G bar here, yeah, and there is this gain K here whose variation is resulting in the root locus, right. So suppose this is what the situation is, this is Y of S, this is R of S, right. Okay. Now this is the system that I am interested in studying, suppose, but you see this transfer function, as I shown you, the way it appears here, this immediately in and of itself cannot be applied to study the root locus. So in order to study the root locus, I better apply minus G, yeah, this is the form that I need. But if I want to apply minus G, I cannot just apply, applying the root locus to minus G and applying the root locus to, minus G bar and applying the root locus to G bar is not the same, right. So then what can I do? What I can then do is I can translate this system to this minus G bar, and let me make this also minus K, okay. So this is plus, this is minus, right. So this becomes the system, Y of S, R of S. Now it is the equivalent system, no, because I have multiplied both by a minus 1, so there is no difference essentially between these two. But now I have a problem on my hands. You see, root locus is going to tell me I am interested in closed loop pole locations as K varies between 0 and plus infinity, that is minus K varies between 0 and minus infinity. Now here is the trouble, because now you see I have cast this transfer function in the conventional form, so I have put it in this typical product form, but in order to do that I have had to accommodate this negative sign. Why did this negative, so let us retrace the steps back. Why did this negative sign come? This negative sign came because the physical system appeared in this form, I could not help it. Why did the physical system come in this form? The physical system came in this form because most physical systems have a DC gain that is positive. Why do most physical systems have a DC gain that is positive? Because we want our systems to respond to a input, a positive input with a positive output and a negative input with a negative output, okay. So that retraces our logic. So now we are now in a situation where it seems like whatever we have learned, very careless of me, this should be positive, no, because I have taken the minus sign to the other side with the express purpose of being able to write this in the standard form for a root locus, which is this S minus Z. So obviously I multiplied by a minus sign here, so there should not be a minus sign here. Again a very careless mistake on my part, but anyway I hope you see the point that now we have this minus G bar. So then it is the same as K times G bar is the same as minus K times minus G bar, right. So therefore when K varies from 0 to infinity, minus K varies from 0 to minus infinity, so all of that is still fine, it is just this one careless little mistake that I wanted to sort of correct. So, suppose k bar is equal to minus k. So, now the root locus problem changes from studying the root locus for variations of gain over 0 to infinity to 1 over minus infinity to 0, right. Now, the problem changes. Now, if that changes, this actually hits at the very heart of root locus. Why? Because remember, what was the angle criteria? The angle criteria said that at any point on the root locus, it must have a total angle of those phasors that I drew that must sum total to an odd multiple of 180 degrees. But now, that was based on the fact that this gain k was positive. But if the gain k is now negative, then that fundamental angle criteria itself changes. How does it change? The angle criteria now becomes thus changes. It then leads to this summation of the theta zi, that is those phasors drawn from the open loop zeros to a particular point on the complex plane, minus the summation of the theta pi's, yeah. This is now going to be some even multiple of pi, okay. Remember earlier it was an odd multiple of pi. So, now it is going to be some even multiple of pi. So, m is equal to 0, 1. So, in some textbooks you will find that this root locus is called complementary root locus. In other textbooks you might find this called the 0 root locus. So, remember they call the conventional root locus as the 180 degree root locus because it was an odd multiple of 180 degrees pi, and this one is basically a multiple of 0 degrees or modulo 2 pi. So, it is 360 degrees, 720 degrees, so on and so forth, right. So, this is also called the 0 root locus or called the complementary root locus, and clearly you see that there are several in and of itself. You might often be interested in studying how the root loci change when gain is varied over a negative range of numbers. That will immediately lead to this study of complementary root locus. But even apart from that, you see, even if you are just interested in studying how the root locus changes, right, how as this gain k is varied over a positive number, if you encounter a non-minimum phase system, that is a system which has a, let us say, one single right half plane 0, the moment you encounter such a system, you will have to know how to draw this complementary root locus. So, let us quickly go over in our heads. I will not be writing it down in details, you can read it up from standard textbooks, but quickly go over the rules. Let us try to think of which rules will change because of this change in this fundamental angle criteria. Number of branches, no reason to change. You still have the degree of the denominator polynomial the same. So, there will still be n branches if the degree of the denominator polynomial is n, or if there are n open loop poles, okay. Number of zeros, open loop zeros, finite open loop zeros is m, right. So, n of those branches will terminate at m of them, and the remaining n minus m, sorry, m of them will terminate at those m zeros, but n minus m of them will have to go to infinity. So, remember we are varying it from 0 to minus infinity. So, the direction in which you draw the arrow head depends on what convention you are considering. Are you considering the convention to be such that k changes from 0 to minus infinity, or are you considering the convention as k changing from minus infinity to 0? If you are considering the convention to be that k changes from minus infinity to 0, then notice that as k tending to minus infinity, the branches start at the open loop pole, open loop zeros, right, and as k goes to 0, yeah, as is usual in the normal root locus, as k goes to 0, they end at the open loop poles. So then the arrowheads will start from the open loop zeros and end at the open loop poles, right. So of course some of them will start from infinity. If it's a strictly proper or a biproper system, then you have more poles than zeros, more open loop poles than open loop zeros. So obviously m of those branches will start at those open loop zeros, finite open loop zeros, but n minus m of them will start from infinity. Along which directions? Well, of course that will change. That will now change because of this angle criteria. So the direction of asymptotes changes. Number of asymptotes does not change. Alright. Location of intersection of the asymptotes does not change because the angle criteria has nothing to do with that derivation, if you recall. Okay. So what have we figured? Number of branches doesn't change. Number of branches starting at the open loop poles and ending at the open loop zeros, or the way you consider the convention, right, the arrowheads. As I said, it's a matter of taste. There's no hard and fast rule as such. Okay. So far as you explain what convention you're using, you're fine, right. Okay. So then we saw that the location of the intersection of the asymptotes, that is the centroid, has no reason to change. The directions of the asymptotes nonetheless will change. What about locations on the real axis which are part of the root locus? So now this is the interesting bit, and this also justifies the name complementary root locus. You see, wherever on the real axis you don't have the conventional root locus, on every such point on the real axis you will have the complementary root locus. So I urge you to take this as it's a very easy exercise. You just apply this new angle criteria to the complementary root locus, and you see that now the complementary root locus will be at those points on the real axis to the right of which you have an even number of poles plus zeros, exactly the same argument as we employed earlier, right. So therefore if you take together the sketches of the root locus and the complementary root locus, then the entire real axis is covered, alright. Yeah. So then that is one observation. What about the symmetry? Well, symmetry comes because of the real coefficients of the polynomial. So the root locus will nonetheless always be symmetric, whether it is the root locus conventional or the complementary root locus, right. So symmetry of the root locus is also guaranteed that way. Come to the breakaway points, you still have to solve the same equations, those conditions for repeated roots or maxima or minima of the value of gain k. And again, after you have solved for those points, as in the conventional root locus case, here also you have to check whether every such point satisfies the angle criteria. Which angle criteria? This new angle criteria now. Okay. So again, exactly in the same fashion you solve for the breakaway and break-in points, and now apply the test of this angle criteria to those points. So you will see now every point on the real axis which is a breakaway or a break-in point, which is a solution to those equations, is either a part of the root locus or a part of the complementary root locus. Yeah, because from our preceding argument, note that every point on the real axis is either a part of the root locus or a part of the complementary root locus. So therefore every real solution of that equation which leads to the breakaway and break-in points, yeah, every such real solution is either part of a complementary root locus or part of the root locus, right. So that's another fascinating aspect of it. What about the crossing over from the right half plane? Yeah, now you have to of course apply in the Routh criteria. You have to check, you have to apply that this value of gain k is negative and things like that, right. So then you have to look for ranges of values of k. So if for no value of negative k, yeah, that Routh table first column turns out to have a sign swap, then there is going to be no migration of roots, okay. On the other hand, if there is a negative value of k at which, yeah, one particular row becomes all zeros, yeah, then you will have some migration happening at that point, right. You will have some imaginary axis roots at those points, right. So again, very straightforward, very obvious. The only thing is that this angle criteria changes. So wherever, so you can take this as an exercise, we have discussed fair bit in the last few lectures, revisit that and at every such derivation just plug in this new condition for complementary root locus, and exactly the way we have derived all the conditions for root locus, apply it to complementary root locus. Same thing applies to angle of arrival and angle of departure, right? So everything just remains the same. So now with that sort of knowledge at our disposal, let us now try to complete the answer to this question, right? So the other day we studied what happens to a second order system with the addition of a pole on the left half plane. We saw that it's detrimental because the root locus gets pushed to the right. What happens with the addition of a 0 to this root locus? Well, it gets pushed further to the left, so it is an improvement, right? So we'll only consider stable systems, so the poles are always going to be in the left half plane, but the 0 can be allowed to be in the right half plane. So what we are essentially trying to revisit is this particular question. Only that we are now going to apply this complementary root locus idea. So how is that? Notice that this is your poles, right? So basically you have, say, s minus z omega n squared, and you have a minus sign ahead of it to ensure a positive DC gain, right? So this is the plant whose root locus we are trying to study. So when you are making k positive, then this overall thing is negative. Okay, so or if you absorb this negative sign in the k, right? So if you now call this, put this k here and get this k to absorb this negative sign, then it's basically studying the complementary root locus of this transfer function. So that's how we transform this problem into one of a complementary root locus. So let's see, suppose you have a 0 added, this is the z, yeah, on the right half plane. So how does the root locus change? Now notice, if you have an even number of poles plus zeros to the right of a point on the real axis, then the root locus exists at such points. So 0 is considered an even number, as I pointed out the other day. So therefore, you see the part of the real axis that is this to the right of all these poles and zeros, yeah, this will be part of the root locus, but to the left of this 0, no part of the real axis will be a part of this root locus, right? Now therefore, obviously these fellows have to, one of them has to reach this 0 here as you vary. So k is varied from, or minus k is varied from 0 to minus infinity, because k is varied from 0 to infinity, okay. That is the same as minus k being varied from 0 to minus infinity. So that is why we are studying the complementary root locus, yeah, clear about that, right. So now notice, what then does this, what option does this branch of the root locus starting here at k is equal to 0 have as k decreases and goes all the way to minus infinity? You know, at minus infinity one branch has to go here. So that is the convention I am following. I am plotting from 0 to minus infinity, so that is the arrowhead. So obviously if these fellows have to go to the other side, they cannot go through the real axis, yeah, because any point on the real axis at these locations is not a plausible point on the complementary root locus. So then it stands to reason that this must migrate in some way like this, and therefore there must be some break-in like this. At the same time here, of course there must be some break-in like this, yeah. So here remember, if you are trying to minimize, look at it as a minima and maxima of the k, right. So notice that this is at k is equal to 0, this is at k tending to minus infinity. So it is as if k is reducing, right. So from here onwards, if you go to this direction, k keeps reducing, and here also k keeps reducing. So this is the maxima. So this break-in point now, yeah, this break-in point is now, instead of a minima, it's a maxima. So that second derivative condition of the testing whether it's a break-in and a breakaway point now changes, yeah, that's a subtle point. But anyway, even we don't even need to evaluate all of that. We can just do a qualitative analysis and see what happens. So even through a qualitative analysis, it turns out that what we may now deduce or what we may now infer is that a right half plane 0 such as this or a non-minimum phase 0 clearly has a detrimental effect on the system, just like a pole on the left half plane pushed the root locus to the right, but of course it pushed it to the right and it went along the asymptotes, right. But here it does not even go to the along any asymptotes, it only goes along this 0 degree line here, that is the one asymptote, but the other branch terminates here. So for any value of k beyond this, let us say this is k crit, so at k crit this crossing over happens. So for any value of k beyond this k crit, you cannot really increase the value of k or decrease the value of minus k further, right. So therefore this is a very important lesson to be taken home, that for non-minimum phase systems particularly, yeah, there will always be this upper bound on the value of k, right. So for non-minimum phase systems, remember why do we want high values of k? Refer to the earlier lessons we had on this study of steady state error and stuff like that. From that we learned that the higher the value of this k, the lower is your steady state error. We want to minimize the steady state error. So one sort of a naive idea is to give as high a value of k as possible, but now from these stability considerations, because when we studied the steady state errors we assumed that somehow or the other system is going to be closed loop stable, but now we cannot withhold that discussion. Now we have Routh array, now we have root locus, we have such detailed tools and sophisticated tools at our disposal. So now we can make these conclusions that in general just having a handle over this k to reduce this steady state error may not be such a good idea, which is what motivates us to seek integral action. Okay, one thing is of course integral action like magic gives you 0 steady state error to a unit step, even if your plant is type 0, right. But even if you say, okay, I am not so concerned about ensuring absolutely 0 steady state error, very small errors will do. So why go for integral action? After all, integral action means there is got to be addition of an integrator. So it's a dynamic controller. What if I just use very high values of static gain k? It's an easy controller to tune. So right, so I'm just going to use a very high value of k. I don't mind very small negligible steady state error. Okay, I'm not that finicky about ensuring absolutely perfect 0 steady state error. After all, steady state only happens asymptotically in any case, right. But even then, now you see there is a fallacy in that argument. Given any arbitrary system, at least this root locus and all our preceding studies of root locus have shown us adequately that you may not be able to increase this value of k to as high a value as you please. Okay. So this kind of forces our hand into looking for dynamic controllers involving integrators and differentiators and stuff like that. We will see that shortly in maybe a lecture or two about how to design controllers to ensure that your performance is up to the mark. But yeah, but now for now you see that it suffices to at least register in our minds that this root locus gives us a very good handle over a qualitative analysis or assessment of different kinds of systems. See, I have not given any numerical values here. Just based on the rules of root locus, I have sketched this rough plot of what the root locus might look like. I mean, for all I care, this might have actually gone like this, yeah. I don't really care. Of course, things are generally nicer, but I don't really care. They are both telling me the same story, which is that beyond a certain value of k, you better be careful because the roots, the closed loop poles are going to migrate to the right half plane and remain there thereafter. Why? Because you have this right half plane 0 in the system. Alright, let me tell you, this right half plane 0 occurs pretty often in very practical systems such as canard controlled aircrafts. Okay, so if you want to study that, that's a fascinating aspect, how this action happens. So basically one feature of this right half plane 0 is, if you recall from our studies earlier, we've seen that there is an initial undershoot. So even though the final steady state value is like in the same direction as the applied input, but the initial response is in the opposite direction. So this is a trademark feature of a non-minimum phase response. Okay, so we've already gone over this, we've already studied this, we've already shown you this, that this indeed happens, right. So right, so you will encounter, the lesson is that you will encounter these non-minimum phase systems in practice, such as even canard controlled aircrafts, and then you will have no option, because it is a mechanical design, you will have no option but to deal with such systems and then consider this complementary root locus, and hence it is good to be aware of how to sketch the complementary root locus side by side with the conventional root locus. Okay. So there is another special kind of a system to which you can apply this root locus technique, although it is not really a rational transfer function. So consider, we visited this earlier also when we talked about the Smith predictor. So consider a time delay system. Yeah. So typically a time delay system would have something like e to the minus st times some gs. So obviously this part is going to be the rational part, that is the ratio of two polynomials. But this part is not rational. So it seems like root locus technique cannot be applied here. That is not quite true. Now you see, if you want to apply the angle criteria, there is nothing really stopping you from applying it to this, is it? You see, what is the phase of this? This is after all a pure exponential, right? So if you want to draw the phase of this, for instance, how do you draw the total phase of this? For example, you have the rational transfer function. You want to figure out if this point lies on the root locus, you have certain poles, certain zeros like this. So you draw the angles of these phases here. So you compute this angle, you compute this angle, and you compute this angle. So this is theta z1, this is theta p1, this is theta p2, right? So then you evaluate theta z1 minus theta p1 minus theta p2, and you check if it's an odd multiple of pi. Yeah, and if this is true, then you say that this point does indeed lie on the root locus. But now, in addition to this, you have this additional factor as well, right? So what is going to be the phase of this particular, what is going to be the phase contribution of this fellow over here at this point? Yeah. So you think about it, if you want the accurate expression for this, what exactly do you need to do here? You need to pass this s point. So suppose this is the point s. So you need to pass this s through this function e to the minus st, right? You need to pass this s through this function e to the minus st and find out its phase, alright? Yeah. So that way you can find out what the phase of the function is. But let us say we will not do that, since we are so familiar with rational transfer functions. So then recall that we had spoken about this Spade approximation. So we will now take a closer look at this Spade approximation. There can be several Spade approximations. So you can call it in general P, let us say QR is a Spade approximation. Spade approximation of e to the minus st such that e to the minus st can be given by some n e s upon d e s, where degree of this NES, so these are polynomials, okay. So this is an approximation, so this is the Spade approximation, right, of this, and Spade approximation of the form QR implies that the degree of the numerator polynomial is Q and the degree of the denominator polynomial is R. So I will just show you what this P11 basically looks like and how to do it. If you are interested in higher order, you can actually take that as an exercise and try out any particular value. The way to do that is you expand both of these fellows in a series. So you consider this NES upon DES to be equal to, say, B0 plus B1S upon 1 plus A1s. Remember, recall that I am not using this A0 here. Why? Because after all, I can, if it's non-zero, I can always divide this, right? So I don't really need this. I don't really need to bother about this coefficient A0. Okay. So I'm not approximating by an integrator. So therefore, this one term is a constant term, right? So I can divide it by. I'm just scaling it here. Okay. All right. So now this can be expanded, if you permit me, in the Maclaurin series using 1 minus A1s plus A1s whole squared minus A1s whole cubed plus so on and so forth. Yeah, if you permit me to do this. And on the other side, notice that the exponential series can be written as 1 minus st plus s squared t squared upon factorial 2 minus s cubed t cubed upon factorial 3, so on and so forth, right. Now what it turns out that how many unknowns do you have here? 3. So we are going to equate coefficients on both sides, so we need up to 3 coefficients. So obviously if you choose pad A of a higher order, right, so again it's going to be strictly proper, of course. So q is going to be always less than or equal to r. Okay. So now of course if you want to make this strictly proper, you better have as many equations as the number of unknowns. Now if you want to do that, then you have to expand up to that many terms suitably. So in my case here, I just have 3 unknowns, so 3 equations suffice. So I'll only expand till the constant term, the coefficient of s and the coefficient of s squared. So you see, if I now collect together all the terms like this, on the left hand side I have b0, of course I'll ignore the higher order terms. What's the coefficient of s? It's minus b0 a1 plus b1 s, right. So b1 s minus b0 s. And what about the excuse me, that should be a minus, and then let me pull out the s from here. Yeah, so I can pull out the s from here, right, because I'm just pulling out the negative sign as common. So it's minus b0 a1 plus b1, right. And about the coefficient of the s squared, it's basically b0 a1 squared, that's between this and this, right, and then between this and this there is minus a1 b1 s squared. There's no other way I can get s squared here, right, constant with the squared term, coefficient of s with the coefficient of s term, right. So of course there will be other terms on both sides, but I am not going to bother about the other terms. So I am just going to concern myself with 3 terms on either side. So immediately I can write that b0 is equal to 1. That follows from, so let me link this up. This is the green one equated with this. This is the blue one equated with just this. Yeah, so I am ignoring the minus sign on either side, and then I have the red one, which is this, equated with t squared by 2, right. So I am going to use the knowledge of the fact that from the first equation I have got b0 is equal to 1, so I am going to plug in this b0 is equal to 1 here. So the second equation then turns out a1 minus b1, because b0 is 1, so it's a1 minus b1 is equal to t. So the second is a1 minus b1 is equal to t, alright. And now the third term, again I am going to use the fact that b0 is 1, so it's a1 squared minus a1 b1, right. So it's a1 squared minus a1 b1 is equal to, of course I remember it's t squared by 2, yeah, it's t squared by 2. So it's t squared by 2. So I have these 3 equations, 3 unknowns. Of course one is already known here. What about the second one here? So now notice that in this equation I can pull out this a1, and then it becomes a1 minus b1 is equal to t squared by 2, but this I know from here, so I am going to just plug in this a1 times t is equal to t squared by 2. Yeah. So now this t cancels because t is not 0. Of course, if it's 0, then it's not a time delay system after all. So that tells me that a1 is equal to t by 2. So if a1 is equal to t by 2, then what is b1? So a1 minus b1 is equal to t, so t by 2 minus b1 is equal to t. In other words, b1 is equal to minus t by 2. So my approximation for e to the minus st, this pad a11 approximation turns out to be 1 minus st by 2 upon 1 plus st over 2. Now notice that this immediately introduces a right half plane 0. Yeah. So even an approximation of this, so let me put this approximate symbol here. So even an approximation of this time delay term, and even if you take higher order pad approximations, you will still see this is a recurrent feature, right. So a time delay term is always approximated by a rational non-minimum phase transfer function. So one way of obtaining these non-minimum phase transfer functions is if the physical model itself governs it, like a canard controlled aircraft. The other way is if you have some semblance of a time delay which can reasonably be then approximated by a rational transfer function, it will always involve such right half plane zeros in the open loop. Therefore when you put them in closed loop configuration, you will always have this gains migrating to the right half plane at some point. Yeah, so that is something to be wary of. So that is the reason why this complementary root locus assumes a lot of significance. It's more important than maybe it's made out to be in many textbooks, where it maybe gets just a passing mention. But I think that it's worth our while to sort of go through all of this, maybe not me in this course, but you should definitely make it a point to go through all of the points that we've discussed about root loci and apply them to complementary root loci by using that modified angle criteria. Okay. So one final point that we want to discuss in today's lecture before we conclude, and from the next lecture onwards we shall talk about controller design. Of course we've already seen some hints about what a good controller should have. It turns out that if you want stability, a good controller better have some zeros, right? Because we've seen this additional 0 on the left half plane, of course on the left half plane, not on the right half plane. So if a good controller has a 0 on the right half plane, left half plane additionally, then it has the effect of pulling the root locus as if more to the left half plane, right. It turns out that such controllers are called lead compensators, okay, or derivative controllers, proportional and derivative controllers, PD controllers, okay. But we'll study more of those, we'll see them in somewhat more detail, and if time permits we'll also probably see a simulation example of designing a compensator for a system, but that's for a later lecture. In today's lecture I would like to wind up by mentioning another critical aspect. This is something that we've already heard of, a term that we've already heard of, but I just want to revisit that term in the context of a root locus. Recall that sensitivity, so if you have y is equal to fx, some function, then you want to find out the sensitivity of y with respect to x. Yeah, I don't remember what symbol I used then, but then how do you go about this? Okay, so what the way to do that is, you take this, for example, this sensitivity. How do you define this? Let's just revisit that term again, right? So you have the sensitivity of this y with respect to this x. Okay. So how do we define this sensitivity? Notice that you already have this y changing, which is basically f of x. So this can be given by fractional change, remember, fractional change in the parameter of my interest. So that's fractional change, rather maybe I should not use this, I should use the initial definition. So the fractional change in y divided by the fractional change in the independent variable. So that eventually leads to this del y upon del x into x upon y. Okay, this is a general definition of sensitivity, just recalling what we've already seen earlier. So this is going to be nothing but delta f of delta x times x upon f, right. So this is the sensitivity. So of course this y is equal to nothing but f. So now in the context of root locus, why is this important? Notice for example something like this, yeah. So suppose you have this additional 0 here and you are designing a controller, right, something like this. So your root locus is going to be something like this, as we have seen earlier. Of course it is symmetric, even if it does not look from my horrible sketch, but you should know that it is symmetric by now, right. Okay. Now notice that this is at k is equal to 0 and this is as k tends to infinity, right, and this is some intermediate value of, let us say, k1, some intermediate value here is k2, some intermediate value here is k3, okay. Now suppose I want to change this k to have some desired performance. What do I mean by a desired performance? Desired performance means that I basically want this maybe this system, the closed loop system, to have a certain damping, yeah. So what is a constant damping line? So let us say this, okay. So now suppose I change this k3 and increase it till I get to k1. Now at k1 clearly I will be satisfying this damping criteria because I will have more damping than I require. At k3 I have less damping than I require, alright. So this line is telling me that my roots better be within this sector in order to meet the damping criteria. What is the damping criteria? It is basically nothing but another way of translating the percentage overshoot. If you recall our discussions earlier, you would know that damping ratio is clearly related to the percentage overshoot alone, right. So now clearly if I have increased my k3 sufficiently, I will meet this condition, but the question is how much should I increase k3, yeah. So how sensitive is this segment of the root locus? In other words, if I make small changes in k here around this point, yeah, around this point if I make small changes in k, will I have a sufficient amount of change in the location of the pole? So the question is how sensitive is the closed loop pole to changes in k, alright. It may happen that for, let us say this is k is equal to what should I say 50. So notice that for going from k is equal to 50 and let us say this is k is equal to 80, but this is suppose k is equal to 1000 hypothetically speaking, okay, just suppose some such root locus exists, okay. So then you see it does not take a genius to figure out, it is really a kind of not much of thought is required for this to infer that you look at this amount of change in the closed loop pole, it is this much. So by changing this k value from 80 to 1000, you only managed to change the location of the closed loop pole by this much, but in changing the value of the k from 50 to 80, you manage to effect almost an equal amount of displacement of the closed loop pole. In other words, around the value of k is equal to 50, your root locus or your closed loop pole is more sensitive to changes in k than it is to changes in k around the value of 80. There is obviously no need to assume, no reason to assume that this changes in k, because after all it is not a linear system, no, this plot is not linear. So there is no reason to assume that for equal changes in the value of k around every value of gain, here there will be an equal change. In fact it can't be. For instance, the most extreme case, for example, take here, it can't be. See, at some point here this k crit, it breaks in here. Now between k crit, if you look at the right side branch of this on the real axis and the left side branch of this on the real axis, you see between k crit to infinity there is only so much change. The entire range from k crit So consider between k crit to infinity the right hand side branch and k crit to infinity the left hand side branch. The right hand side I mean this one, this branch, and the left hand side branch I mean this one, right. So the left hand side branch goes all the way from this point, a finite pole, to infinity, but the right hand side pole only has a finite distance to traverse. So obviously it stands to reason then that this segment of the root locus that is on the right hand side is less sensitive. So you have to make a lot of changes, you have to make huge changes in the value of k in order to move this pole even slightly. But on the other hand, on this side, if you make small changes, it will probably go up in leaps and bounds. Okay, so this is the same motivation that guides us to ask questions like, for example, you have a system like k upon s plus 1 into s plus 2 into s. Okay, so suppose you want to study this system's root locus, and suppose a typical question could be that study sensitivity around k is equal to 20. How do we do it? So how are the closed loop poles given? In order to understand what the closed loop poles are, you have to obviously solve for this equation, k into s plus 1 is equal to 0. So I better divide this then by with respect to s, no, because remember I need after all what is my performance metric here? The closed loop poles are my f here, no. So this closed loop poles have this property that they satisfy this equation. So let me take, so s is a closed loop pole since it satisfies this equation. So let me now differentiate this with respect to k. So this is going to be s squared plus 2s plus ks plus 1 plus k is equal to 0. So let me now define, so this is 2s ds dk plus 2 ds dk plus s dk that is 1 plus k ds dk plus again this k differentiated with respect to itself is 1 is equal to 0. So from this I get that ds dk, which is basically nothing but proxy for this delta s upon delta k, right, which is nothing but this delta f by delta x. So now this is going to be given by, if I am not mistaken, by minus of s plus 1 divided by 2s plus 2. If I am not mistaken, just please check this, I am not sure about the calculations, I am doing it in a hurry, but nonetheless you should be able to convince yourself that this is correct. So you differentiate the, yeah, it is s plus 1, yeah, I guess it is correct, yeah, I think it should be right, 2s plus 2 plus k, yeah. So this is going to be my function here, right. Now how do I evaluate this s? So remember that this sensitivity is going to be given by this ds dk times k upon s. So obviously k I can plug in this value of 20. How do I know this s? Well, I just simply solve this equation, yeah, and I get two closed loop poles because I plug in k is equal to 20 here and I solve for the two poles. I think the poles would come out to be somewhere near, if I computed correctly, around minus 21 and minus 0.95. Those are my approximate calculations I had done some time back. So please check, those are going to be the roots of this equation when you plug in k is equal to 20, right. So around this you plug in these values of s and plug in the value of k is equal to 20, and ds dk of course you again plug in the value of s is equal to minus 21 or minus 0.95 as the case may be, depending on around which branch you are trying to look at the sensitivity. So there is going to be obviously two branches, one at s is equal to 0, starting at s is equal to 0, one at s is equal to minus 2, okay. So this is how you go about the problem, okay. So I hope that you found this to fit in with the picture of sensitivity that we had discussed earlier. Please try to practice this and complete this problem as part of an exercise and find out what the sensitivity of the poles are, okay, around this. And as an addendum question, suppose delta k upon k is equal to 0.1, what is delta s upon s, okay. So take this as an additional exercise, okay. Thank you, that will be all.